Thank you for watching this video. This is just at least to give some information on the lab classes, especially the metal testing part of the lab class. This was used to be conducted face-to-face, but because of many reasons, we used to run this one online. Yeah. But these slides will give you at least a bit of information on what is that part of the lab session. Okay, so tensile testing of metals is part of the construction materials course, I think. As you see, this the contents of this document is introduction to tensile testing, and there is basic principles of tensile testing, the Australian standard for tensile testing, then what are the equipment used, how test preparation of the sample, what are the quantities or parameters monitored, and then mechanical properties that you get from the result. When we say tensile testing, it means, as you see in the picture, it is just to pull, as if as you see the rope is pulled, just to pull or to apply pull force on the sample generally. So the applied load and the extension values are monitored. So you apply load or force, then you monitor the extension. This type of test is static by nature. The load is applied at low rate of loading or rate of strain. Load, some people call it load or some people call it force, but force is basically the actual term, the force applied on the sample. Load can be a general term, like for instance, you can't say load for a stress as well, or other types of load, but when you say force, it will clearly tell. So the precise term is better to call it force. So why do we need to do tensile tests? Sorry. To select materials for engineering applications. So in order to select the good type of materials that are good for engineering applications, different engineering applications, you need to know the property of the material, and the property of material can be obtained after you tested it. So one of that is tensile test. The other is to ensure quality in material specification. For instance, when factories produce materials like steel, they need to make sure that their quality is as per their specification. So to keep or to maintain their quality, they have to make sure they do tensile testing every time from each batch of from their products. The other is to develop new materials. So when you develop new materials, you have also to do tests to make sure that the material is the new material is as per your requirement. The other is to predict the behavior of material under different forms of loading. For instance, tensile test is like uniaxial tension. You apply the load along the center or mass of the sample. But this test helps you to understand or investigate to the behavior of the material, and also you will know or you will predict also how it will behave in other forms of loading. Always remember, we have to refer standards when we do tests. Standards are very important. If we don't have standards, we will not have a baseline or the same reference. So when we compare results, if we don't have the same way of testing method, very difficult to compare results. So make sure that you follow standards so that you have consistency, reliability on your test results. For instance, some of the tests that is conducted is for quality assurance or quality control. For instance, if you see this one is a specification from, I think this is from Blue Scope, or yeah. So when they give this specification, when you buy reinforcement bars, they give this specification. When they give this specification, what they are saying is their steel has a grade of this steel, has minimum yield strength stress of this one, it has the strength of this one, and elongation of this one. So when they claim that their steel fulfills this requirement, they have to make sure that they do testing at certain time from each batch of the production to make sure what they say is as per, and the result is also similar to that. Example of this one, for instance, this is a typical test that was conducted in ETS many times ago. So these are steel racks. These similar steel racks, you see them in Bani and other warehouses. So for instance, in these steel racks, this was a project done by ETS for an industry. So if you see these steel racks, this is one of the part of the steel rack. So if we take section of that, then from that we also strip or cut from here that test piece. You see, you take from the rack, then you also you take from a section, then from that section you also cut a sample, a test piece. So that is how test is done. So if you see this test sample, this is a flat plate sample, then when a load is applied, this is load versus crosshead travel. So crosshead travel is where the machine moves. The two crossheads of the test machine move apart. So this shows a general trend of the curve. But what is important is the stress strain curve of the sample. So this was a typical result of this test one we were doing. So if you see, this is stress and strain. So the stress strain is what is needed. So when we do tensile test, we are planning to plot the stress strain. From the stress strain, we get all the necessary mechanical properties. The Australian standard is usually the ones we refer when we do testing in Australia. So this is one of the standards, AS 1391, and it's called metallic materials tensile testing at ambient temperature, ambient at normal temperature. There are also tests at elevated temperature, but this standard is at a normal temperature. It means the laboratory is normal temperature, like 23 degrees centigrade with around 55 to 60 humidity. The temperature and humidity of the lab environment where you do the testing is also very important. You have to recur the temperature, the humidity, as well as also the gravitational force of the area. As you see here, the standard has a lot of information. It describes the method by which the test piece metal is trained, like room temperature. It defines the proportion determined. The standard also tells you what proportion you need to determine. It defines also the term used in describing that. It also defines the terms used, how you use the terms, what type of symbols you use. It specifies the dimensions of standard test piece. The standard also suggests or tells us what dimensions of the test piece should be, if it is flat, if it is round, if it is unmachined. Specifies the method of tensile testing as well. It also specifies the method of tensile testing. It specifies the type of equipment, the type of testing machine you use. The symbols used for various dimensions and properties are taken from the symbols in these slides are taken from the Australian standard. As you see now, this is a typical test piece, which is a dog bone shaped test piece. See the question, what is the reason for reducing the cross-sectional area of the gauge section relative to the rest of the specimen? Why do we reduce the cross-section along here relative to the overall section? Okay, It's alright, that's it. So in order for the deformation and failure to be localized in a region of high stress concentration, when we measure the specimen like this, what we are doing is we are concentrating the stress around here. So when we concentrate the stress around here, we are trying to make the material or sample to fail around this area. Failing around this area helps us a lot because we are putting the gauge lengths around this area. Okay, so it helps us to measure also other parameters. So all these dimensions are specified in the standard. So you have to refer the standard to fit the overall length, distance between shoulders, the gauge lengths, the diameter, the radius of fillet. This is the radius of fillet or the radius of transition where stress is transferred from here to this radius section to this curve. So make sure that this is the right curve. What are the equipment used when we do tensile testing? We have a ruler, digital caliper. Ruler is normal ruler that you know. Digital caliper is digital with most of these calibers are 0.01 millimeter. Micrometer is like 0.001 millimeter. Usually we use a digital caliper to measure the gauge length, while we use a micrometer to measure the diameter of the sample. Extensometer is electrical equipment. It has inbuilt strain gauge inside. So this extensometer will help us to measure the extension of the sample. This extensometer will be attached to the sample. Strain gauge is also another equipment. Sensor. This strain gauge is glued into the sample and it measures the strain. So this strain gauge measures the actual strain. Extensometer measures only the extension. So you have to divide by gauge lengths to get strain. But we use a strain gauge. It gives you a strain. You don't need to divide to get strain. It is a strain by itself. And there is also another equipment called LVDT, which measures the displacement. In all the equipments, the one here in this slide, the test machine has an LVDT that measures the crosshead, the movement of the machine platforms. And you need also a test machine, of course, with a computer data logger or controller. So these are the equipments that I mentioned: the ruler, digital caliper, micrometer, extensometer attached on a sample, old mechanical extensometer attached. This mechanical equipment people use it to read continuously so that they record manually. But nowadays, this one records automatically. You record at certain frequency or certain time. So LVDTs are these ones, and strain gauge is the one stuck on sample or you glue on the sample. Extensometer is an instrument that measures the specimen to characterize strain. So the extensometer helps us to measure the strain. Okay, so the name comes from extension meter, simply extension device. As you see now, this is the extensometer attached on a sample. Okay, the extensometer is clipped onto a sample, but there are other types of extensometer nowadays. We have also in our lab digital image correlation equipment, which works with camera. There is also video extensometers in some labs as well. But strain gauges are attached to the sample itself, and you have an amplifier to measure the strain, and you get directly the strain on the sample. So if you use a strain gauge, you get the strain on the sample. Then the other equipment you need testing, tensile testing machine, the testing machine itself. So for example, this is a universal testing machine. Universal means it can do tension, compression, bending. It is universal. Some test machines are only tensile testers. It means you can only do tensile, but this machine you can also do compression, bending by changing the test rate. So if you see the test sample is in here, and the extensometer is attached into it, and this is the old dial reader. Nowadays we have a new dial reader. Requirements of a testing machine. What is the test machine required? The testing machine should have a sufficient force capacity. So this is very important. the test machine should have sufficient force capacity. It should be able to test the sample. For instance, if the sample is 50 kilonewton, the test machine should be more than that to test. The other is control of test speed. The test machine should be able to control the test speed, because when we apply load on the sample or force on the sample, when we pull the sample, we have to pull a certain load. Are we applying kilonewton per second, which is load rate, or millimeter per second, which is displacement rate, or are we applying strain rate? So there are three different types of loading systems that we use. The machine should have also precision accuracy. So the machine should be accurate and precise. And this is done by calibrating the test machine. Okay, external companies come and they check the test machine that it is in good working condition and the load is the true load. It's essential in tensile testing to control the rate of force applied. So always when we do tensile tests, we have to make sure that we apply a rate of force at certain. For instance, it can be load rate, which is kilonewton per second. It can be strain rate, which is dimensions per second. Or it can be cross-head rate, which is the separation of the grips or the separation of the testing machine cross-head body. If you see load rate means kilonewton per second or kilonewton per minute, it's not difficult to use load rate, and also not easy, difficult to use cross-head rate. Cross-head rate is millimeter per minute. Just you tell the machine to apply a load at certain millimeter per minute or millimeter per second. But strain rate is a bit difficult because there should be a loop system between your strain reader and the machine, which is a bit sophisticated equipment is needed to use the strain rate. But what usually done is an equivalent strain rate can be done using cross-head rate. That is usually what we do in our labs. Three types of force application device. So generally, the types, if we come to the types of testing machine, they can be like hydraulic oil-filled cylinder and ram. They can be gear-driven or screw-driven type. They can also be lever and counterweight type. So hydraulic are those ones with high capacity most of the time. Screw-driven testing machines are with most of the time low capacity. So the strain rate defined as the rate at which a specimen is deformed, which is controlled within the test. So strain rate is when you apply the load by monitoring the strain. It means you apply load based on the response of the sample. That is the reason that makes this type of test complex. But cross-head rate, which is millimeter per minute or millimeter per second, you apply simply load just as a normal separation rate of the test machine crossheads, which is uniform. You don't base on the response from the sample, but strain rate, you need to get a strain reading from the sample, then do loading. So this is typically a test machine looks like. For instance, this one is the screw-driven type. The screws are here, and this is the crosshead, and these are grips, pneumatic grips. Actually, these ones you need compressed air to use this type of thing. And this is also another type of test machine. This is upper crosshead, lower crosshead, and the test machine table. There is a hydraulic piston here with oil, and this pushes up and pushes this one and pulls the sample. So during the test, this stays constant or fixed. And this is the controller. So this was the old test machine that we had before. But this one is very important to understand, because the new machine is an automated system where you don't see what's happening, but this one tells you what's happening. For instance, the red one shows the maximum force, while the black one shows the instant force. when load is applied, both of them, they will increase or they will move. But as soon as you reach a maximum force, this red will stay there, while the black will return back. For instance, when you reach maximum force and the sample start to neck, reduce in cross section, you can clearly see the black one going backwards. I mean, the load will be reducing, while the red will be staying on the maximum force. So that's the reason I just left this slide instead of changing it into a new system. So the red is showing the maximum force, and the black shows the instant force. And there is also a digital display where it shows the reading, the actual reading during the test. So what types of test pieces we have for shapes? We can have round test piece, rectangular test piece, or reinforcement bar also be tested with that. These two are machined. If you see, they are machined. Machined means to look like a dog bone shape, but this one is unmachined. There are also different type of grip devices for different applications. They can be thread grip types, can be split grip type, V-shaped. Depending on your sample, you can have different types of grip, because you have to make sure that you grip the sample properly. Otherwise, if there is no good grip, the sample will slip and your result will not be good. So you have to make sure that you have a good gripping device. The gripping device, one, it must fit the specimen properly, hold the specimen. The other must have also sufficient force capacity to avoid damage during testing. So the grip device should have also very good hardness, should be hard enough to resist the damage from during testing. So as you see, these are the clamping methods. These are mechanical wedges, and these are you see the teeth, okay, or the jaws. So, and this is pneumatic type. Gauge length. Gauge length is very important to understand what gauge length is. Usually, gauge lengths are use gauge marks to measure the gauge length. So the gauge length is a section of a sample where the measurements are done. Okay. Gauge marks. We put gauge marks. Gauge marks are lightly punched or scribed in the center prior to the testing and are separated by distance known as gauge. So what we do is we mark these 2 points, then we measure the distance between them, and that is the gauge length between the marks. Okay, the Australian standard suggested or recommends to use this formula to find the initial gauge length. So what you do is you have the cross-sectional area, square root of the cross-sectional area multiplied by 5.65 gives you a gauge length. Then you go and mark on your sample. For instance, if it is 10 millimeter sample, if you put 10 millimeter, a cross-section of 10 millimeter in here, usually the sample diameter we do testing. So 5.65 multiplied by the cross-sectional area square root, you will get a gauge length. Usually the gauge length for a 10 millimeter is 50 millimeters. So around 50 millimeter your gauge length. Then you mark the gauge marks. Then these gauge marks will help you to measure the initial before the test and the final after the test. And the extensometer this is the extensometer attached on the sample with some clip. The extensometer has its own gauge length. The distance between these two, this is 50 millimeter, 50.000. So the initial gauge length is 50. So whatever data you get from the extensometer, which is the extension data or the elongation data, which is in millimeter, you divide it by the this initial gauge length, which is 50, you will get the strain. So there are different types of extensometer. This is electrical extensometer, but there are also mechanical as well as optical or video test records. What are during the test? What do you do or what do you record? Okay, so the physical measurements we need to have is, for instance, you measure the gauge length, original gauge length. The original gauge length is the distance between these 2 points. Okay. Then after the sample is tested, you also measure the final gauge length. You bring the 2 broken samples together. If you bring them together, fits them, and then you measure, that will be your final gauge length. Then you also have to measure the initial diameter and final diameter. Usually, when you measure diameter, it's better you measure 3 times by rotating the sample, so that at least you have an average of an average diameter. Final mean diameter is the same. So the measurement of diameter, initial diameter, and final diameter will help you to measure the cross-sectional area before and after. That will help you to calculate the percentage reduction in cross-section, while the gauge length, the initial and final, will help you to measure the percentage elongation, which are the ductility measurements. So from these measurements will help us to measure the ductility, tensile strength, yield strength, proof stress. What about the load data? The load data, usually we get it from the machine. The machine will log the data, the applied force on the sample. Then from the data, we will get the maximum load, which will help us to get the ultimate tensile strength. We will get the fracture load, will help us the fracture stress, to calculate the fracture stress. We get also proportional limit load and yield load. The yield load can be yield strength or proof strength, depending on the type of meter. Then the extensometer gives us the elongation or change in length or extension, which will help us to find the strength. This is just put for discussion. What are the failure patterns of those different materials? If you see this curve, this is the stress strain. Our aim is to develop the stress strain curve from the tensile test. So this is just a discussion. If you add carbon, what is the advantage and what is the disadvantage? So you can easily see from this curve, especially in terms of strengths, as the carbon increases, how the strength changes. Now, in this lab, usually tensile lab classes, usually 2 samples are tested, mild steel and cast iron. This is just to show students the difference between ductile and brittle materials. So when you do ductile material like black mild steel or mild steel, which is low carbon steel, you will see this type of curve. Okay, as the test progresses, the sample passes through series of steps like elastic region, then it yielding, then starts to go into a strain hardening region. It reaches maximum force, then starts to give up, and that is making where you see physically the cross-section is reduced. So from this graph, stress strain graph, you determine the modulus of elasticity, the yield, lower yield and upper yield. This is upper yield, this is the lower yield. Okay, you can see the definition for a yield. Usually the lower yield is the yield of yield stress. Then you have the ultimate tensile stress, UTS, and then you have fracture stress. This region is elastic, while this is plastic. Elastic means if you stop the test at this stage, the sample can restore its shape back. But if you stop the test at this stage, the sample will not restore its shape. It is permanently deformed. So this type of ductile black mild steel, as you see, has a linear relationship between stress and strain. It's not linear. Then starts to form after plastic deformation and non-linear. But initially it has a linear until it reaches its proportionality. So this has linear elastic behavior. It obeys Hooke's law. Obeys Hooke's law means the stress is proportional to strain. Then the other important from this graph is it has defined upper and lower yield point. And the fracture stress, as you see, is also less than the intimate tensile strength. What are the properties determined from this test? From the load versus extension diagram, you get yield load, maximum load, failure load. But from the engineering stress strain curve, remember it is engineering stress strain curve. If it is true stress strain curve is different. True stress strain curve, we have to use the instantaneous cross-sectional area to plot the curve, but that's not easy. So what we have is engineering stress strain relationship. And what it means is the stress, to get the stress, engineering stress, you are divided by the cross-sectional area. Although practically the cross-section radius every time, but here we are assuming the cross-section, the original cross-section is used throughout this. That is the reason engineering stress. Then you get from this stress strain curve the modulus of elasticity, upper and lower yield strengths, proof strengths in terms of cast iron, and you can also get modulus of toughness and modulus of resilience from the graph. From the physical measurement, the measurement that you do before and after the test, the gauge length before and after, the diameter before and after will help you to measure the ductility, which is percentage elongation and percentage reduction. What are the fracture patterns? When you see ductile metals, with metals, mostly low carbon metals, the mode of fracture is like you see. It is a cup cone type. Cup cone means one is like a cup, the other is like a cone. And it has also silky appearance. Okay, so the other important fracture pattern that you observe in ductile metals is neck. They will neck before they snap. They don't snap or they don't break suddenly. There is necking, which gives you enough information or enough time to prepare that the sample is going to break. So as you see, this is before the test, then this is after the test. There is necking, there is massive elongation. And you see it was here, then extended this much. So that makes it extended along the same another sample. If we see cast iron, it's different. Cast iron is high carbon metal. There is high carbon content in cast iron, and the behavior is different. If you see all the test processes are the same, but the stress strain behavior of the sample, as you see, it is curved. Curved means non-linear. It is curved, non-linear elastic behavior. It does not obey Hooke's law. There is no linear relationship. There is no defined upper and lower yield point. That's why we have to use a proof stress to determine the yield. And cannot clearly identify between fracture stress and ultimate. As you see, because it just reaches maximum force and snaps, it's very difficult to have a defined fracture stress and the ultimate tensile stress. What are the properties determined maximum load, failure load? From the engineering stress strain relationship, we will find the modulus of elasticity, which is the slope, and proof strengths in terms of cast iron, and the percentage of elongation and percentage of reduction area, as well for ductility. So if you see cast iron, if it is hardly you see elongation, and there is almost none reduction area, just it snaps. Brittle fracture exhibits bright and crystalline surface in appearance, no significant reduction in cross-section. There is no, almost difficult to see physically the change in diameter. So as you increase the carbon content, for sure, you see, as increase the carbon content, the strength also increases. So it's good also to see the effect of pure aluminum versus aluminum. So pure aluminum is very soft. Aluminum alloy, a bit of strength, good strength, and better stiffness. Mildly versus cast iron, you already saw it here. What about if we test steel reinforcement? Are the steel reinforcements closer to mildly or cast iron? Of course, steel reinforcements are ductile. They have very good ductility. So these are some of the things that we need to discuss. What is the tensile test procedure? Sketch the fracture patterns, plot the load versus extension diagram, then plot also the stress strain diagram, then determine mechanical properties, and also discuss what is the engineering significance of those two samples. Which one is good for engineering applications? This is a typical test data. For instance, when we do testing, we measure the initial and final diameter. We also measure the initial gauge length and final gauge length. Then after the extensometer has 50 millimeter as the initial gauge length. Then when we do the test, we have a cross-head travel, which is simply the movement of the cross heads of the test machine in millimeter. We have load in kilonewton, and we have extension measurement from the extensometer in millimeter. So these three parameters, three data will be collected. From the data, you can easily plot the load versus cross-head travel. This shows you the overall trend of the test, okay, how the sample generally behaved. From this, you can find the maximum load, you can find the fracture load, then you divide the maximum load by the cross-sectional area to get the ultimate tensile strength or the tensile strength of the sample, denoted as RM in the standard. The fracture load or fracture stress, you divide the fracture load divided by the area, you get the fracture stress, which is this one. Remember, this is load versus cross-head travel. It's not stress strain diagram. Remember, it's not a stress strain diagram. If you see the stress strain, this is also load extension. This is load versus extension. This is the extension is the reading from the extensometer. If you plot load and extension as it is, you only plot this one as it is, this one and this one, without dividing anything. So as you see, the extensometer is removed at this one to avoid being damaged. And this is more than enough to do calculations of your mechanical properties. This is where you get the lower yield. You find from here the lower yield load. This lower yield load, you divide it by area, you get the yield strength of the sample. Upper is this one, the upper force, here upper yield force divided by the area, you get the upper yield stress. It is the lower yield stress or the lower yield stress that is given as a yield strength of the sample, just for your information. Then the youngest modulus or modulus of elasticity of the sample is usually the slope of the stress strain. Now, from the load extension, you divide the load by the area, and you divide the extension by the initial gauge length of the extensometer, which is 50, you get this curve, which is stress strain. This is our aim is to find the stress strain curve. The stress strain curve only reached here because we removed the extensometer. So as you see, if you calculate the stress here, the slope here, which is the change in stress over change in strain, you will see the modulus of elasticity or youngest modulus, which is around 200 for steel. And you can also find the proportionality limit of the sample where the linear behavior changes. The other parameter that you get from the test is measure of ductility. Ductility is measured by percentage of elongation and percentage reduction in area. Simply what you do is you measure the initial and final gauge lengths that gives you the elongation. Initial and final diameter will help you to calculate the area, which gives you the area impact. So these two are the measure of ductility. You can also measure the toughness and elastic resilience of the sample from the curve. So generally, the modulus of toughness is the total area covered. The same process also applies to cast iron, except the same data, except the way the youngest modulus is calculated is different. Because it is non-linear throughout, so you cannot use the upper and lower yield strengths to get the yield. So instead, you have to use another method, which is called the secant modulus. As you see, the stress strain is plotted, then you divided the maximum tensile strength into 4 sections. You get the 4 sections, you touch the 4 sections on the curve, then you draw a line, tangent line between to this point. Then that will give you the secant modulus of the sample. So you get, instead of the slope of the stress strain diagram for a linear like mild steel here, because curved you have to find the slope between these two. That gives the secant modulus, and you report as secant modulus. And for yield, you have to use proof stress, which means you have the secant modulus, this one, then you draw parallel to that line starting from 0.002, which is 0.2%. So this is proof stress at 0.2%. Then you draw parallel to this line, and you catch this point is your proof stress at 0.2 strain. You can have also a proof stress at 0.5 strain. At 0.5, you directly draw a line, straight line, not parallel to this line. For 0.5%, just straight, then you get 0.5% strain. But this one is parallel to the secant modulus line. Modulus of toughness is the area. You just calculate the area, the total area, gives you the modulus of toughness of the sample. Feel free to comment if you have any question. These are generally the reinforcement steel, where it's used in the pumping concrete. These are the types of reinforcement bars used in Australia. 250N means normal ductility, 300E means earthquake, 500L means low ductility. So R, D, I also are the another round shape, D deformed shape, I indented shape. So different types of reinforcements. If you refer this standard, all these details are specified. These are the shapes. Based on the shape, if you see the shape, you can easily say, is it 250N, is it 500E, or 300E? You can easily say from the shape. And this is another information. These are structural steel, different types of structural steel. Hot rolled versus cold rolled. It's good also to understand what is hot rolled and cold rolled. Thank you for watching. I hope this gives you a bit of information. Feel free to comment if you have. Thank you.